My name is Alex, and I'm very grateful for the organizers for the chance to speak here. I'm now broadcasting from Zurich. It's actually also a very intense heat wave here, so I probably feel your pain. And the topic of my presentation will be about vision transformers. I will talk about two recent papers that we wrote. One is about scaling up vision transformers, and the other one is about...
Alex, can you stop a little bit? I got the audio cut out. I think, okay, can you say something again?
1, 2, 3.
Yeah, okay, let's continue.
Okay, and the second paper will be about unifying vision transformers for the tasks beyond image classification. So first, since it's the first talk of this workshop, I wanted to quickly give a reminder about vision transformers. So that's the vision model that was recently introduced at the ICLR 2021 conference. And it is a joint work of many of my colleagues and myself. So the vision transformer model is the surprisingly simple and effective adaptation of the transformer model for the raw images. The idea is very simple. You start from the input image, split it into patches. Then you project all of these patches using the shared linear projection to the one-dimensional, to the 1D representation of some fixed length. And you also append learnable or fixed embeddings that encodes the positional information for each patch, such that we can later differentiate between different positions. We additionally introduce an extra token that corresponds to the that is essentially called class token, and we use it to read out the representation for the final prediction. And after that, we apply the most standard transformer encoder model that is used in the NLP field. And we read out the final representation through the MLP or a single linear projection to produce the final class. So that's very simple model. One thing I want to stress is that the main component in the transformer is the self-attention operation. This is the global operation that processes all of the image patches simultaneously, starting from the layer 1. And here on the left, I have an image that shows how the central patch interacts with all other patches in the input image. For example, in the first row, there are multiple attention heads, and each attention head attends to essentially lots of patches. They can be nearby, like for the first one, or it can attend to the patches in the other parts of the image, which is in strong contrast to convolution, can model the global interactions, while convolution will only attend to very local contexts. Now I want to quickly introduce the notation that I will use throughout the talk. So the model is called vision transformers, or VIT for brevity. We also encode the model size using some shortcuts. For example, VIT base stands for the standard model, which has 86 million parameters and 12 layers.
Sorry, and Alex, your audio is cutting out a little. Could you speak more into the microphone? I believe it's probably something on your end. Oh, is this? Oh, okay. Well, try again.
Okay. I doubt it's my microphone. That's the one I was using for a very long time.
Okay, yeah, I have to hold the audio jack. I guess it's on our end.
Okay. So yeah, essentially we have three main model sizes: base, large, and huge. So the base one has roughly 86 million parameters, and huge one has more than 600 million parameters. If you see the slash and the number after the model name, the number corresponds to the size of the patch that was used to train the model. So for example, with L16 means that the model was trained with 16 times 16 patches. And when we put all of this together and pre-train the VIT-H model on the JFT dataset with 300 million images and then transfer it to ImageNet, we get the new state-of-the-art result on ImageNet. So that's it for the quick reminder. Like now I want to present a more recent paper, which is about further scaling vision transformer beyond the width H model. It's a relatively recent paper and it's published at the CPR conference, and it will be presented soon at the main conference. It's called Scaling Vision Transformers, and it's a joint work with Shava, Neil, and Luca. So quick spoiler, so we scale the model from H to with G. We again get the ImageNet SOTA. So with G stands for with giant. So let me now explain the main components of our recipe that led us from with H to with G. So first we were wondering whether 300 million images is enough to pre-train the model, or we will actually benefit from even larger data set. So we conduct relatively small scale study where we try to pre-train the relatively small vision transformer models with B and with L on the 3 billion images instead of 300 million images. And the result is quite consistent and clear, is that when we switch the data set, we get slightly better results on all our main metrics. So the dashed lines on this plot show what happens if you pre-train on JFT with 300 million images. And then the solid lines show what happens if you increase the dataset size. So it's like it's quite simple step, and we just commit to use the larger data from now on. Then the next more complicated question is how to fit larger model onto device. So how to go beyond the width H size, because width H was pretty much at the limits of the TPU memory, and also without going model parallel. So because of this, we try to hunt for extra memory to fit the larger model. One thing that is important about TPUs is that if you train your model on TPU, TPUs will be very happy if all the intermediate tensors have the dimensions which are multiple of 128. So in this case, it nicely fits the TPU hardware memory devices. But unfortunately, like we actually have 256 patches for our typical model, but because we have the extra class token, it results in the 257 patches, which is like as bad for TPUs as it can be, because the TPUs will then pad the tensors we have to the next multiple of 128 and result in much higher memory consumption. So naturally, we look into eliminating the class token. So instead of using the class token to read out the representations, we infer the representation from the patch tokens. And we try to compute global average pooled representation of all patch representations, or global max pooling, or the specialized multi-head attention pooling. So in the end, it turns out that all these heads work roughly the same, and it's the same as using the class token as well. And we decide to go for the most flexible and general one, which uses the attention pooling inside. And then we save the memory because of this. And now we have exactly 256 tokens in our model. The other pain points for memory is the optimizer. So normally researchers use Atom to optimize transformers. And Atom, for each parameter that you have in your model, Atom requires 2 more extra parameters for the first and the second momentum. So if your model has size M, then you need 3 times M memory on your device to store the extra parameters needed for Atom. So this is why we look into alternative optimizers. And in the NLP literature, there is a popular ADA factor optimizer that is should be similar to Atom, but use only negligible amount of extra memory on top of the memory needed to run your model. Fortunately, we empirically observed that it doesn't really work for vision applications, so we were getting very unstable and bad results. So we revisited it, and we found 2 modifications that actually make it work again. One is to reintroduce back the first momentum, but in half precision. And the other one is to disable some additional learning rate scaling that was introduced in the other factor. And with these 2 modifications, we actually make it work exactly like Atom. And in the end, it will consume 1.5 times M memory, which is already much better than 3 times m. So with all these modifications, we try to fit the larger model. One interesting thing is that we use XLA, which is the compiler for machine learning programs. And XLA is very smart and powerful and can optimize the memory footprints very well. But because it's so complicated, we don't really know in advance what model will fit, what model won't fit. So instead of just trying random configurations, we decide to try all of them. And we just run each configuration for a single step. If it works, then we just mark that it works. And if it fails with out of memory, we mark that it fails with out of memory. And we produce this nice plot. So for example, the orange cells show which configurations work when we use the original bit recipe. So for example, like for 32 layers, it shows all the cells that work. And on the x-axis, we have the MLP width. On the y-axis, we have the embedding dimension of the transformer. With our modifications, we go from the orange frontier to the blue frontier. So now, as you can see, we can fit many more models. And in the end, we decide to go for this cell, which is we call width G model. It corresponds to the 48 layers with the hidden MLP dimension of 8,000 and the embedding dimension of 1.6,000. And the final thing is that we need to set up our learning rate scheduler to train the huge model on the huge data. And the big pain point here is that we don't really know in advance for how long we will be able to train our model, because we need a lot of resources, and also these resources are not reliable. They may break, or maybe we get an extension to use these resources for longer, maybe not. So it's like a lot of uncertainty. And in the end, we may have 2 or 3 or 4 weeks. Very problematic because of this to set up the learning rates, because all the standard learning rates schedules, they expect that you know in advance for how many steps or epochs you are going to train. So inspired by the NLP literature, and in particular T5 model, we use the following recipe. So we train indefinitely with the learning rate that is agnostic of the total length. And the way it works, it is just the inverse square root of the number of steps. So that's the learning rate that we use. And once we decide that we want to finish our job, we very quickly cool down the learning rate from the current value to 0 linearly. And empirically, we did a lot of small-scale experiments, and we confirmed that this scheme, which is commonly used in NLP, actually works almost as well as the other common learning rate schedules that know in advance which learning rates, how many steps are needed to train the model. So our recipe may be a little bit slow, a little bit worse in the end, but it's very close. And also it has a huge benefit that we don't need to commit to any fixed duration in advance. So we put all of this together, bigger data set, bigger model, new learning rate scheduler, and a few other small things that I don't have time to discuss, and we get the new model. So it works much better than the original with H model. So here we show the few-shot transfer performance on ImageNet for 1 shot, 5 shot, 10 shots, and 25 shots. The dashed green line is the old with H model, and the blue line is the new with G model, so which dominates the old model. We also get the new SOTA on ImageNet, ImageNet v2, and VTAP datasets, and on some other benchmarks, we come very close to the SOTA results. Finally, I want to highlight my favorite observation from this paper. So essentially, the larger models are not much better at getting better performance, but they're also more efficient learners. So for example, if you only show let's say you show 1 billion images to your model, then the large model will have much lower error than the base model or tiny model. And this has very important implications that are shown on this plot. So there's a lot of information on these plots. I will just highlight my favorite one, and I invite you to check out the paper to read more from this plot. So in the color, we essentially encode the size of the model. So the red colors correspond to the larger models, the blue colors correspond to the smaller models. And on the x-axis, we have the total compute used to train the model. On the y-axis, we have performance measured like as ImageNet few-shot transfer. And what we observe from this plot is that for a given amount of compute, for example, like here vertically, the red models achieve better performance than the blue models. So it means that by increasing the model size, you actually can get to better performance using the same amount of compute as you would use the smaller model. So the bigger model can actually save the compute, which is like very counterintuitive at first. Yeah, that was it, the first part. Now I want to switch to the second part of the talk, which is about unifying vision transformer model to tackle vision tasks beyond simple image classification. So let me maybe first motivate this part a little bit. I would like to argue that modern computer vision models are very complex and fragmented. For example, if you consider the task of object detection, a very recent popular model called DETR looks like this. So it has the convolutional backbone that additionally has the transformer encoder. Then it has a fixed number of object queries, transformer decoder, then matching loss, and 4 different heads. And it's like not all the components that I used there, but it's like very nice model. It works really well, and it became really popular recently with like lots of follow-ups. But if you look at the best and most well-performing follow-ups, they look even more complicated. So they introduce new components, some upsampling mechanisms, and so on. So it takes a lot of time to keep up with even like a single task in computer vision. Or if you prefer slightly different flavor to object detection and, for example, use faster CNN models, there's like yet another set of tricks and components you need to implement to make it work. And things get worse when you jump to another task. For example, if you want to do polarization, then there's like yet another set of models you need to implement. Same goes for depth prediction. There's like a ton of components you need to take care about, and so on. So I think this is not ideal, and we need to push towards like more unified setups to handle with problems. So maybe the first question we can ask ourselves is, why not the simple thing? So why cannot we take the let's say our favorite model, for example, vision transformer model, and just use it to map the inputs to the outputs? For example, if it is a colorization task, we can just map grayscale images to the colorized images. Or if it is an panoptic segmentation mask, we can map RGB image to the panoptic mask. So here I show the actual outputs of what happens if we just train the plane width model for these tasks. As you can visually see, it doesn't really work. So for example, the colors are not consistent and the panoptic mask is flickering. So what is the problem here? The problem here is that this base model is very good at predicting per pixel classes and per pixels like probabilities, but it's not capable of coordinating decisions. So for example, for this bell pepper, it's not sure whether it's green or red, and it's just flickering between these two colors. Or it's not capable of capturing the notion of instance ID, where it doesn't matter which ID you assign, but it only matters that you get the consistent ID within this instance. And this essentially justifies the complexity that I just shown before. So all these components are typically introduced because of this problem that you need to some structure to your output. So the next question we can ask ourselves is, what is the minimum amount of extra work we can do to make this base model actually work universally for all or like most of the vision tasks? And the high-level idea that we propose in our paper is to introduce so-called guiding codes. So imagine you have a magical oracle that would condition the model on extra piece of knowledge. For example, for the colorization task, it would say that on the left, all bell peppers are red, and on the right, all bell peppers are green. It will be much easier with this small piece of knowledge for the model to produce the consistent colors. And the same goes for panoptic. If the magical oracle would just give a hint that there are 2 elephants in the front with IDs 1 and 2, it is much easier for the base model to produce the consistent non-flickering outputs. So the question is, how do we automate this these guiding codes, the production of the guiding codes for the base model F? And then we propose the following setup. So this is a end-to-end model. We have the base model which maps whatever input to whatever output, and we have this guiding code that is derived from the ground truth through the restricted oracle model, which is just a plain width model. And we train it end-to-end. Empirically, we observed that this model works really well, but obviously it's not yet a useful prediction model because the guiding code is derived from ground truth. So we don't have ground truth at test time, so it's useless model by itself. But what we can do after we train this model, we can freeze the restricted oracle and then train the almighty language model to emulate this oracle from the image alone. And this language was very powerful, so it's autoregressive, and it will model the joint distribution of this code, which is also capable of modeling the complex structure that goes into the image. And when we put these 2 components together, we get the final model. So it has 2 parts: the language model that first takes image as input and then autoregressively produce the guiding code. And then this guiding code will condition the base model to produce the output. And we apply exact same model to the panoptic task, to the depth prediction task, to the colorization task, and everywhere we get quite good results. And when I say exact same model, I really mean it. So the only difference between these models are tiny changes in the configuration file. So we need to configure how to format inputs and outputs because they can be different for different tasks. For example, there are 2 discrete channels for the panoptic task, but there is just 1 discrete channel for depth prediction, and for colorization we output 3 continuous channels. So that's like what we need to configure. And also we may slightly change the loss if the task is continuous, like colorization. We use mean squared error, but we use cross entropy for the panoptic task. And some small hyperparameters can be different, like learning rate and epochs. But otherwise, everything is exactly the same. So results are shown here. We don't yet match this state-of-the-art results on all of these tasks, but we match state-of-the-art results as of like 2 or 3 years ago. So the results are very decent, and we still believe that they can be improved a lot with further modeling improvements to this general model. Okay, so I'm almost done. So I just wanted to quickly demystify this model a little bit. So the model is quite simple, except maybe for one part. So when I say that we train this thing end to end, it may be not clear how to do it because we have a discrete bottleneck here in the middle of the model, and naturally it doesn't have any gradients defined for it. So it's not clear how the restricted oracle model can be trained. So luckily, if you look closely, this part in this purple region is exactly the VQVE autoencoder. And there is a very nice paper that explains how to train such model. So the high-level idea is that whatever you have, whatever output, whatever you encode the outputs, you discretize it using some fixed dictionary. So essentially, you match each output to all the words in this dictionary, and you use ID of the closest word to discretize it. And then you decode it by just matching the ID to the corresponding embedding. And the way you train it, you just use the straight-through gradient estimator. So essentially, you pretend like there was no discretization, and you just pass the gradient from the decoder to the encoder. With like few small extra tricks to enable dictionary learning, it actually works really well, and you get this discrete representation, and you can train it essentially end to end. So yeah, that's everything that I wanted to talk about. Just as a quick reminder, the Scaling Vision Transformer paper was published at the CVPR conference, and you are welcome to visit our poster on Thursday in the morning. Thank you. And I am ready to take questions if there are any.
Okay, thank you, Alex. So if there are any questions, please come to the mics, and also for virtual attendees, please leave them in chat. We'll get to those. Any in-person questions? Let me check the chat. Okay, I don't see any questions in chat. So I had one quick question. So the optimization recipe that you covered in the first part, have you also tried it on different frameworks like BIT, normally on VITs? I guess just curious if those are VIT specific or do they generalize to other architectures as well?
I think not really. So what I know is that other fact is successfully used in NLP applications, and it's different from our implementation. And I think personally we have not tried it for other models, so only tried it for vision transformer models. So yeah, I don't have unfortunately any empirical evidence for you here.
Wait, another question?
Hey, Alex, thank you for the presentation. I have a question on the unified VIT. With the unified model on different tasks, what's your take on multitask training for the unified model?
Yeah, that would be the next step, which we'll probably make or somebody in the community. So now we have a very powerful model to tackle any of the vision tasks. And there are essentially no blockers to apply it to many problems at the same time. So we are only like slightly bottlenecked by the data, but this we also plan to solve in the future.
Okay, one last quick question, maybe the virtual question. So we have the, hold on, let me scroll on. I guess people are curious about the intuition of this, training for the continuous code. Can you, I guess, talk a little bit about that, maybe in particular for the depth estimation problem, like how these learned guides are helpful for the model?
Yeah, so the intuition is that when you introduce this guiding code, it enables your model to model the interaction between your outputs. So as I shown initially, if you just have the base model and you, for example, want to produce the colors or you want to produce the depth, it will focus on getting each individual pixel correctly. But it's not capable of modeling the interactions of neighboring pixels or pixels across the image. But when you introduce this guiding code component, it is the autoregressive model, and it outputs each code autoregressively. So it is able to coordinate the decisions which it puts in this guiding code. And this helps to add the structure to the model. So for example, when you do colorization, you get smooth colors. Or when you do depth prediction, it is also capable of making sure that your depth is not jumping abruptly. So you will get also smooth depth maps that are visually more appealing and look more plausible, as opposed to using just the plain model that won't care about neighboring pixels having the same depth, for example.
Okay, yeah, thank you for the excellent talk. Let's thank the speaker again.